Hello, my name is Joanna Ledesma. Today we'll explore one of the foundational ideas of topology. How can we describe the shape and behavior of sets on the real number line? More specifically, we'll investigate what it means for a set to be open, closed, both, or neither. At first, these ideas seem abstract, but they appear all around us in scheduling, engineering, geography, and science. Before we begin with the mathematics, let's look at a few real world situations where these ideas naturally arise. Imagine school starts at exactly 8 a.m. Suppose someone says, be here around 8 o'clock. What does around 8 mean? Maybe it means around arriving 7:55 and 8:05. Notice that we've naturally created a boundary. There is an inside region, there is an outside region, and there are questions about whether the endpoints belong. Keep that thought in mind. Consider a completely different situation, a child's temperature. Doctors often define a safe range and a range that requires concern. Suddenly, boundaries matter again. Is 101 degrees included? What about 96.7? The answer affects how we classify the situation. Once again, we're thinking about regions, limits, and boundaries. Now let's move to something even larger. Geographic information systems, transportation networks, and utility planning all rely on boundaries. The image here shows a donut-shaped region defined by two circular boundaries. The question becomes, which location belongs to the region? Which lie outside? Which lie exactly on the boundary? These questions determine how maps, transportation systems, and utilities are analyzed. Notice the common theme. Whether we're talking about schedules, temperatures, or maps, each example is really asking which boundary points belong to the set and which do not. Topology provides a language for answering exactly that question. Most of mathematics, before real analysis, focuses on computations. We measure distance, solve equations, and manipulate numbers. Topology shifts our attention from numbers themselves to the structure of sets. Instead of asking, what is this number? We ask, how is a point related to the nearby points? This changes in perspective. It's one of the major ideas behind modern analysis. To discuss closeness, we first need a way to measure distance. Well, a metric provides exactly that. On the real number line, distance is defined by d of xy is equal to the absolute value of x minus y. A valid metric must satisfy three properties: identity, symmetry, and the triangle inequality. Once we can measure distance, we can begin discussing what it means for points to be near one another. This slide shows the roadmap for the remainder of our journey. We begin with distance. Distance allows us to define neighborhoods. Neighborhoods allow us to define interior points and limit points. Those ideas lead us naturally to open and closed sets. Finally, we connect these concepts back to real-world boundaries. Here are the first tools of topology. Neighborhood is simply all points within some distance r of a point P. An isolated point stands alone. A limit point is different. No matter how small a neighborhood we draw around it, we always find other points of the set nearby. These ideas will become the building blocks for open and closed sets. Rudin introduces a collection of definitions that form the language of topology. Today, we will focus primarily on four: neighborhoods, interior points, limit points, open sets, and closed sets. The remaining ideas, such as dense and connected sets, will appear briefly near the end. Before we can define an open set, we need one more concept: the interior point. Notice that point P has a neighborhood that remains entirely inside the set. No part of the neighborhood crosses the boundary. I like to think of this as a safety zone. The point has room to move in every direction without leaving the set. Formally, a point is interior if some neighborhood around it is completely contained in the set. Now compare that with a point near the boundary. Every neighborhood around that point touches the set. No matter how much we zoom in, points of the set continue appearing nearby. This is the idea of a limit point. Limit points help us identify where a set accumulates or approaches its boundary. We are finally ready to define an open set. A set is open if every point is an interior point. In other words, every point has a safety zone around it. Notice that the endpoints 0 and 1 are not included. They're missing. No matter which point I choose, I can draw a small neighborhood around it that lies entirely within the set. Even if I move extremely close to 0 or 1, there is always a tiny neighborhood that remains inside. This is why I call the boundary the unreachable edge. We can get arbitrarily close to the boundary, but the boundary itself never belongs to the set. In Rubin's language, a set is open if every point of the set is an interior point. While open sets avoid their boundaries, closed sets do something a little bit different. A set is closed if it contains all of its limit points. Here, the endpoints are included. This time, the endpoints belong to the set. Closed sets are not defined by neighborhoods. Instead, they are defined using limit points. Imagine a sequence of points moving closer and closer to 1. Since 1 belongs to the set, the limit never escapes. That's why I describe closed sets as a solid wall. Every limit point is captured by the set. Nothing leaks out. Once we understand open and closed sets individually, we can begin diagnosing familiar and unfamiliar sets. Topology is often described as a study of open sets, but in practice, we spend a lot of time asking, is the set open? Is it closed? Is it both? Or is it neither? Let's examine a few. Example 1. The interval 0, 1 is open because every point is an interior point. Example 2. The interval 0, 1 is closed because in this case, it contains all of its limit points. Example 3, 0, 1 is neither. It excludes one boundary point, but it includes the other. So it fails both tests. Example 4, the entire real line is both open and closed. The key question is always, what happens near the boundary points? Let's revisit our original examples. The school schedule corresponds to an open interval. The transportation boundary corresponds to a closed region. The temperature example is neither. And lastly, here's a new real-world application of both. The universe stretches infinitely in all directions. These abstract definitions are actually describing everyday situations. These examples show that topology provides a language for describing real-world boundaries. Up to this point, we've mostly worked with intervals, but topology applies to many other types of sets. Intervals are only the beginning. Topology extends far beyond that. Connected sets describe spaces that stay in one piece. Dense sets describes collections where points are everywhere. These ideas become central later in real analysis and finally, topology allows us to analyze much more complicated sets. Take any point in the set. Ask, can I draw a neighborhood around that point that remains completely inside the set? For the union 0, 1, 2, 3, the answer is yes. Every point has a neighborhood contained in one of the intervals. Therefore, the set is open. The rational numbers fail this test. Every neighborhood around a rational number also contains an irrational number. So no neighborhoods stay entirely inside the rationals. The natural numbers fail for a different reason. Around any natural number, every neighborhood contains non-natural numbers. Therefore, the natural numbers are not open. Notice that the same simple question works for every set. Can I find a neighborhood around each point that stays completely inside the set? All right, my topology detective, you've been assigned 3 top secret activity files to investigate the boundary behavior. Your mission? Determine its topological state. Is it open? Is it closed? Both or neither? Use your knowledge from today's lesson. Make sure to read carefully the rules of engagement and the required evidence. Statements of open, closed, neither or both are not always enough. All right, you got this.